The concept of infinity isn't just an abstract idea floating in the realm of mathematics. It's a shape, a structure that stubbornly refuses to be confined by our usual ways of thinking. Imagine a universe where infinity isn't endless in a vague sense, but a tangible form you could, in theory, encounter, study, and even explore. Today, we're diving into the hidden architecture of infinity, how it exists as a framework, a blueprint of what infinite really means beyond just never-ending. If you've ever wondered what infinity looks like when approached as a physical structure rather than an abstract concept, you're about to see it in a whole new light. Defining infinity as a conceptual framework. In mathematics, infinity is often regarded as a kind of boundary that signifies unboundedness, but when approached as a structure rather than an abstract notion, it transforms into something more tangible and operative. Think of infinity not as a vague or elusive concept, but as a framework that can be embedded into the fabric of geometric forms, topological spaces, and algebraic systems. This perspective allows mathematicians and scientists to explore how infinity shapes the very architecture of mathematical objects, rather than merely representing an endless extension. For example, the idea of an infinite grid or lattice introduces a structural certainty. The grid extends without end in every direction, providing an infinite yet structured environment for analysis. Such frameworks serve as tools to understand the behavior of systems at scale, especially those that are too vast or complex to comprehend through finite models alone. From a more conceptual angle, defining infinity as a structure involves examining how infinities can be classified and related within hierarchical systems. Cantor's theory of different sizes of infinity exemplifies this approach vividly. He demonstrated that there are countably infinite sets, like the natural numbers, alongside uncountably infinite sets, such as the real numbers within an interval. These distinctions establish a hierarchy or architecture of infinite sets, revealing that infinity isn't a monolithic idea, but a layered and organized structure. This layered structure provides a framework that begins to resemble a vast, interconnected web where infinities have specific relationships, sizes, and properties rather than existing as amorphous or purely abstract concepts. Visualizing infinity as a structure opens avenues for exploring complex phenomena in physics and cosmology, especially in scenarios where infinity plays a fundamental role in the shape of space and time. The notion that the universe itself may have an infinite extent becomes a question of the geometric and topological structures that could underpin the cosmos. Certain models consider infinite yet curved spaces, like the E8 lattice in string theory or the infinite tilings that fill Euclidean and hyperbolic planes. These structures suggest that infinity isn't just a boundary to be approached, but a core component of physical reality, woven into the very design of the universe. In this sense, infinity becomes a blueprint or pattern that informs the structure of reality itself. In essence, defining infinity as a structure encourages a shift from viewing it as a mere boundary or limit to recognizing it as a deeply ingrained aspect of mathematical and physical architectures. It involves understanding how infinity builds relations, hierarchies, and symmetries within systems, transforming it from an abstract limit into a meaningful component of the universe's scaffolding. This approach fosters deeper insights into how the infinite manifests across different domains, whether in the smallest quantum scales or the vastness of cosmological models, offering a richer perspective on what it means for something to be infinite in a structured, tangible way. Mathematical structures and infinite sets. In the realm of mathematics, infinite sets defy intuitive notions rooted in finite tangible objects. These sets are not just endless collections, but instead are structured entities with properties that make them fascinating and complex. For instance, the set of natural numbers, often denoted by, constitutes a countably infinite set. It's possible to list all its elements in sequence, such as 0, 1, 2, 3, and so on, extending forever without missing any. This countability leads to interesting contrasts with uncountable sets like the real numbers between 0 and 1, which cannot be enumerated in any sequence, no matter how long. The distinction underscores a fundamental difference. Some infinities are bigger than others, a concept formalized through the theory of cardinality. Mathematicians have developed a variety of structures to understand how these infinite sets behave and relate to one another. A prominent example is the power set operation, which takes any set and produces the set of all its subsets. When applied to an infinite set like the natural numbers, the power set results in a set that is strictly larger in terms of cardinality. The power set of, often called the continuum, has the same size as the set of real numbers, highlighting that there are different sizes of infinity. This hierarchy of infinities becomes a key focus in set theory, revealing an ordered structure among infinities that can be compared and mapped onto one another through sophisticated functions like injections and surjections. Further, the concept of infinite sequences and limits provides a way to organize and analyze infinite structures. Sequence spaces, such as the set of all infinite sequences of binary digits, serve as models for complex infinite objects. These spaces can be endowed with topological structures, like the Cantor space, where clopen, simultaneously closed and open, sets serve as a fundamental basis. This construction exhibits how infinite sets are not mere abstract collections, but can have rich internal topology allowing for notions like continuity, convergence, and compactness, all within infinite frameworks. Recognizing these properties helps reveal the internal logical architecture of infinite structures, demonstrating that they can be studied through the same rigorous methods used for finite structures. Ultimately, these ideas point to a view of infinity not as an endless, shapeless expanse, but as a highly organized, layered landscape of mathematical structures. From countable to uncountable sets, from power sets to sequence spaces, the structure of infinity encompasses a diverse array of models with well-defined properties and relations. This approach transforms infinity from an abstract concept into a tangible, intricate framework, illuminating how infinite sets cooperate within larger mathematical universes. The study of these structures continues to expand, providing deeper insights into the fundamental nature of mathematics itself. Infinity in nature and physical reality. In the natural world, the concept of infinity manifests not as an abstract notion, but through patterns and structures that stretch across scales and phenomena. Take the Fibonacci sequence, for example. It appears repeatedly in plant growth, from the arrangement of sunflower seeds and pinecone scales to the spiral shells of mollusks. These spirals often approximate the golden ratio, an irrational number linked to aesthetic harmony and growth processes that seem to extend without clear boundary. Although the plant itself is finite, the underlying mathematical principles governing these arrangements hint at an intrinsic, almost infinite pattern embedded in the fabric of living organisms. Similarly, physical phenomena such as fractals demonstrate how natural structures can embody infinite complexity within finite boundaries. Coastlines, mountain ranges, and clouds all exhibit fractal geometry, where each part resembles the whole at different scales. If you zoom in on a coastline or a snowflake, you'll see similar intricate details repeating themselves infinitely at smaller levels. This self-similar pattern exemplifies nature's potential for infinite complexity. Moreover, in the microscopic realm, the structure of crystalline materials and the branching patterns of lightning exemplify how fundamental physical processes produce structures that visually suggest an infinite extension, even within the constraints of finite materials. The universe itself offers intriguing examples of how infinity is woven into its very fabric. The observable universe appears vast beyond comprehension, expanding at an accelerating rate, with many cosmological models suggesting that space continues infinitely outward or loops back on itself in complex ways. The cosmological principle assumes an isotropic and homogeneous universe on large scales, implying that at some level, the cosmos might stretch infinitely. Although this remains a subject of scientific investigation, the sheer scale and uniformity of cosmic background radiation reinforce the idea that the structure of reality might be fundamentally infinite, or at least extend beyond what humans can currently perceive or measure. While the physical world provides tangible instances of infinity in patterns and scales, it also raises compelling questions about the nature of reality itself. These examples demonstrate that infinity is not merely an abstract idea, but embedded in the very structure of natural phenomena. From the endless spirals of galaxies to the recursive complexity of fractals, nature appears to mimic the mathematical concept of infinity in tangible, observable forms, blurring the line between the finite and the infinite in a way that invites continuous exploration and wonder. Philosophical perspectives on infinite structures. Infinite structures challenge our understanding of space not merely as an expansive universe, but as a fundamental element with inherent geometric and topological properties. Philosophers who explore the nature of infinity often reject the notion that it is just an abstract concept or a mathematical whimsy. Instead, they view infinity as a concrete structure woven into the fabric of reality itself. Think of a fractal, like the Mandelbrot set. Each zoom level reveals more complexity, suggesting that the structure of infinity is recursive, self-similar, and endlessly rich. This recursive nature implies that infinity isn't just a point at the end of a line, but an ongoing process, a kind of structural fabric that threads through space at every scale. Many philosophical traditions have considered infinite structures as more than mental constructs. For example, in certain metaphysical views, infinity manifests in the very organization of the cosmos, an unending hierarchical hierarchy, where each level reflects a larger whole, echoing the notion of a hierarchical infinite regress. This perspective challenges us to think of infinity as a type of pattern or architecture, not just a limit to be approached, but as an active, structural reality. The paradoxes of actual infinity, like Hilbert's hotel, where a hotel with infinitely many rooms can accommodate infinitely more guests, highlight that infinity, when regarded as a structure, has peculiar properties that defy our finite intuition, hinting at an underlying logical and philosophical architecture. In considering infinite structures as tangible entities, some philosophers argue that the universe itself might embody a form of infinity, structured through an infinite web of relations. The idea is that space could be thought of as an interconnected network rather than a simple void. The notion that space is filled with an infinite network of points or densities leads us into modal debates about the fundamental nature of reality. Are these infinite networks merely mathematical models, or do they possess an ontological status? Here, the discussion hinges on whether the infinity of structure exists independently of human cognition, something that can be discovered rather than invented. This conceptual shift connects the realm of philosophy directly with cutting-edge physics, where the geometry of space-time itself may be understood as a kind of infinite, dynamic structure. Further, the contemplation of infinity as structure invites a reconsideration of the boundary between the finite and the infinite. Instead of viewing infinity as a distant horizon, something to be reached or transcended, it can be seen as an intrinsic component of the universe's architecture. Philosophers like Spinoza and Kant have engaged with this idea, suggesting that the infinite might be embedded within the very framework of reality, shaping the limits and possibilities of existence. The view that infinity is a structural aspect rather than a mere abstraction opens up a landscape where the infinite is not a paradox to solve, but a core feature of the world's architecture, demanding new ways of thinking about reality's fundamental layers. Usnovnoy, Razděl 5. In exploring the structure of infinity beyond its abstract notions, one encounters the fascinating concept of geometrical or topological models that embody infinite extension in a tangible way. Unlike the purely conceptual idea of infinity as an endless sequence or an unbounded number line, this perspective treats infinity as a shape with specific properties and inherent design. For example, certain mathematical objects like the Mobius strip or the Klein bottle serve as physical-like representations of infinite or self-referential systems, demonstrating how infinity can be embedded into actual forms rather than just ideas. One particularly compelling example is the hyperbolic plane, which can be visualized through models like the Poincare disk, a finite disk that contains an infinite number of points with a consistent geometric structure. This demonstrates how a finite boundary can contain an infinite complexity, emphasizing that the notion of infinity isn't merely about unending quantity, but can also involve intricate arrangements that reflect infinite extension through recursion and self-similarity. These models challenge traditional notions by illustrating that infinity can have a definite shape, one that conforms to rules and structures, yet still represents an unbounded concept. Furthermore, the concept of infinite geometric structures finds application in diverse fields, from cosmology to computer science. The shape of an infinite universe explores whether space itself is finite but unbounded, or truly infinite, with models suggesting the universe could fold back on itself, creating a closed or multiply-connected space. In computer science, fractal algorithms generate infinitely complex images and landscapes through recursive patterns, which embody the idea of infinite complexity within finite parameters. These representations reveal how understanding infinity as a structure enhances our grasp of the universe, digital environments, and even abstract mathematical spaces. By viewing infinity as a shape, an explicit, describable entity, the notion becomes a tool for visualization and deeper comprehension. Instead of a vague or ungraspable idea, infinity gains form, draping itself over structures that can be studied, manipulated, and even constructed. This approach opens doors to new insights, providing a tangible means to investigate concepts like unbounded space, limitless potentiality, and recursive complexity. It highlights the layered richness of infinity, not just as a concept, but as a physical and mathematical reality with real-world relevance and profound implications. As we've explored, infinity isn't just an abstract idea floating in the realm of mathematics and philosophy. It's a complex structure with shape, form, and interconnectedness that we can begin to understand and appreciate on a deeper level. By viewing infinity as a structure rather than a mere concept, we open new doors to how we perceive the universe, ourselves, and the endless possibilities that lie ahead. Thanks for joining me on this journey into the shape of infinity. First, hope it sparked curiosity and a fresh perspective. If you're fascinated by these ideas, stay tuned for upcoming content delving even further into the mysteries of perception, consciousness, and the universe's hidden frameworks. Don't forget to like, share, and subscribe. It helps connect more curious minds to these explorations. Until next time, keep asking, keep wondering, and remember, infinity might just be within your reach.